Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our review of series. Remember, this is not intended to be your first exposure to these topics, just a review. First up, the alternating series test. Suppose we have a sequence entirely non-negative numbers, but then I make a series where I add in this power of -1. So since ai is entirely non-negative, but it's now being multiplied by -1 to the I or -1 to the I plus 1, those terms will be alternating between non-negative and non-positive, and that's called an alternating series. If the limit of ai is 0, then an alternating series made out of ai will converge. Okay, so remember in the divergence test, in general, if the limit of a sequence is 0, a corresponding series, you really can't determine anything. The alternating series test tells us if the limit of a sequence of non-negative numbers is 0 and you form an alternating series out of it, that series will converge. This is called the alternating series test. So suppose I have a sequence. If I form a series out of the absolute value of ai and that series converges, then a series just formed out of ai converges. Now ai here doesn't have to be negative numbers. It doesn't have to strictly alternate positive, negative, positive, negative. It's just formed out of a bunch of real numbers, some of them positive, some of them not. But if I make a series out of all of their absolute values and that converges, then so would the series made out of the original ai. Furthermore, we get an inequality. The absolute value of the series formed out of ai is less than or equal to the series formed out of the absolute value of ai. When the series of the absolute values converges, we say that the series converges absolutely. If a series converges, but it doesn't converge absolutely, that's called converging conditionally. So the rest of the tests in this lecture are about absolute convergence, to conclude that a series converges absolutely. In other words, that a series formed not out of the original terms, but out of their absolute values converges. First up, something called the root test. Suppose I have a sequence ai. If I take the absolute value of ai and compute the ith root and take a limit of all of that and find that the limit exists and is L. If L is less than 1, the series converges absolutely. If L is bigger than 1, the series formed out of the ai diverges. But if L is exactly equal to 1 or the limit doesn't exist, we're going to not conclude anything. There are, by the way, some refinements about when the limit doesn't exist. It might be possible to get some information, but we're just going to say inconclusive. The root test is very useful if we're forming a series out of things that already have powers. For example, if I'm more or less given by c to the I and I take an ith root of that, those cancel out and we just get out a nice constant absolute value of c. So when your series is formed up of terms that already have powers in them, the root test can be very handy. Another very common convergence test is the ratio test. Suppose you have a sequence of numbers, compute their ratios, ai plus 1 over ai. Because we're dividing by ai, it's important that the terms of this sequence are never 0. Take this ratio, take its absolute value, compute a limit. If you can do that and find the limit is L. If the limit L is less than 1, the series made out of the original terms converges absolutely. If this limit exists and is bigger than 1, the series formed out of the original ai diverges. If the limit is 1 or doesn't exist, the test is inconclusive. And similarly to the root test, there is possibly some information about when the limit doesn't exist, but we're going to lump all of that together. If the limit doesn't exist, we simply say the test is inconclusive. And the ratio test is extremely useful when terms of the series are given by formulas involving lots of different things, powers, exponentials, or factorials. Okay, in the first, we'll have very easy to compute limits, and the other two admit very convenient algebraic simplification that makes the limit relatively easy to compute. So if the terms of your series have powers or exponentials or factorials, the ratio test can be very handy. Let's take those tests and apply them to some examples. First, determine whether or not the following series converges or diverges, -1 to the I over I. Now this series is alternating. 1 over I is always positive, and now I have that -1 to the I thrown in. And 1 over I tends to 0. So we have an alternating series formed out of terms converging to 0. So by the alternating series test, this series does converge. However, If we had taken absolute values, then the negative 1 to the I can be thrown out, and now we have the sum of 1 over I. By the p-test, this is 1 over I to the first. This is also a very special series called the harmonic series, the sum of 1 over I, and that diverges. Therefore, this series does converge, but it does not converge absolutely, and that was what was called converging conditionally. A second example, let's determine whether or not the sum of 2 to the I plus I over I factorial plus the cosine of I converges or not. Let's let AI be exactly the terms of our series, and B sub I is a slightly simpler form. Now our numerator 2 to the I plus I, as I gets larger, that's basically just 2 to the I. And our denominator I factorial plus cosine of I is pretty small, it's in between plus or minus 1. I factorial is much bigger than that. So more or less, we expect this to behave like 2 to the I over I factorial. So that's going to be what we let BI be. So first we're going to compute the limit of AI over BI, and this limit is exactly 1. Okay, so if I divide by BI, we end up with this 2 to the I down in the denominator and this I factorial up in the numerator. Okay, so this 2 to the I can cancel this here as long as I then divide by 2 to the I there. And I'm going to cancel I factorial out of these terms as well. Okay, but then I do have to divide this by I factorial. So this simplifies down to just be this. I over 2 to the I goes to 0. Cosine of I over I factorial goes to 0. So overall, this all just goes to 1. So by the limit comparison test, since the ratio AI over BI had a finite non-zero limit, either both series converge or both diverge. So in order to determine whether the series of AI converges or not, we can instead turn our attention to the series BI. And we're going to apply the ratio test because we've got these factorials and exponentials in BI. So we take the absolute value of BI plus 1 over BI. So our numerator ends up with 2 to the I plus 1 and I factorial, whereas our denominator gets 2 to the I and I plus 1 factorial. That's just this one over that one and simplifying the fractions down. You'll end up exactly here. But 2 to the I plus 1 over 2 to the I is just 2. And I factorial over I plus 1 factorial is just I plus 1. So this ratio, BI plus 1 over BI, is just 2 over I plus 1. And as I goes to infinity, that goes to 0. So by the ratio test, we got out a limit and it was less than 1. It was 0, in fact. Therefore, the series of BI converges absolutely. Since that series converges absolutely, it also converges. And now that we've determined the series of BI converges, our earlier result with the limit comparison test tells us the series out of the AI also converges. Let's do a third example. Determine whether or not the sum of 1 over n over 2 plus 1 over n, all raised to the nth power, converges or not. Now with a little bit of algebra, multiplying numerator and denominator by 2n to the nth power, we can simplify this a little bit to get the sum of 2n over n squared plus 2, all raised to the nth power. Since we have something in parentheses to the nth power, the root test is going to be very straightforward. Also, there are no negative terms in here, so we don't really need the absolute value. So we just take terms of our series and raise it to the 1 over n, and take a limit. Now our nth power and our 1 over nth root will cancel each other out. Now we're just taking the limit of 2n over n squared plus 2, which we very quickly see is 0. Now the root test, when the limit could be computed and was less than 1, tells you the series converges absolutely, and therefore the series converges. So this series converges. To what? I have no idea, but it definitely converges to something. Overall then, what did we do? The ratio and root tests are very powerful and useful convergence tests. They lend themselves very naturally to series where there are lots of powers or factorials or exponentials involved in computing terms of the series. Both of them involve computing a limit L. If that limit is less than 1, you get absolute convergence for your series. If the limit is bigger than 1, you get divergence. And if the limit doesn't exist or is equal to 1, you don't get any information about the series converging or not. Both of these tests will be very fundamental when we turn our attention to power series and Taylor series because powers and factorials arise very naturally in those specific types of series.